In this video, we'll talk about monomials and factoring. So let's review factoring for numbers. Now again, a factor of something. Say we're looking at the number 40. Well, the factors of 40 would be 5 and 8. Or, potentially I could say 2 and 20. Basically, any two numbers that multiply to make 40 are factors of 40. So, before we talk about how to do it with monomials, let's review factoring for numbers. And in particular, let's look at prime factorization. And what this means is that we're going to take any number and break it down to a number of prime factors. So prime, if you remember, is numbers that are only divisible by 1 and themselves. So 1, 2, 3, 5, 7, 9 are examples. 4, however, is not prime because it's divisible by 1, 4, and then 2. It has an extra factor there. So let's just take an example number. Let's say I want another prime factorization of, let's say, 120. Well, there's a few ways you can do this. The easiest way, I would think, would be to just start with a factor tree. So I just think about, okay, what two numbers do I know that multiply to make 120? And you can pick any two that work here. Off the top of my head, I'm thinking 12 and 10. Okay, and then I'm going to look at these numbers and think, okay, what two numbers multiply to make 12 that I know of? Because 12 is not prime. I'm going to go until I get to primes. Well, I know for sure 2 goes into it. 2 is prime, so I can stop on that side. And then 6. 6 is not prime. So I think, okay, 2 and 3. Now, those are all prime, so I'm done on that side. Now I have to do the same thing with the 10. Two numbers that multiply to make 10 would be 5 and 2. And again, both those are prime. So instead of writing 120, I could say 120 is equal to 2 times 2 times 3 times 5 times 2, which, if we follow our laws of exponents, we can combine some like terms a little bit. We could say, okay, this is the same as 2 cubed times 3 times 5. Now this would be the prime factorization of 120. Now these are kind of the building block numbers for all of our bigger composite numbers. And we'll talk about an example here where we're using this for monomials. So if I want to factor monomials, I'm going to do them in a very similar way. So if we think about an example here, let's say we have 40 x cubed y squared, and I want to factor this. Well, there's a couple of ways you can go about it. You can break it up into pieces where you look at just the number, just the x variable, just the y variable. That's fine. Or you can think of it as one big collective piece where then you sort out the variables in particular. So I'm going to leave it in the case where I break it up. So if I think about 40, let's factor 40 first in prime factorization. So I think about two numbers that multiply to make 40. Off the top of my head, I think 10 and 4. Quick and easy. Okay, let's look at 4. That's 2 times 2. Those are both prime, so I'm done there. And 10, again, I have 5 and 2. Both prime, those are done there. So 40 is equal to 2 cubed times 5. Ultimately, when I do my prime factorization, that's what happens. Now, if I think about x, I have no idea what number x is. It might be prime, it might not be. For the moment, let's consider it as a prime number, which means that x cubed is just x times x times x, which means that it just comes along for the ride as x cubed. Same thing for the y. It's y squared. So really, if you're looking at factors of polynomials, it's not really any different than factoring a number. You just have the variables come along for a ride. Now we'll talk about an application of factoring here where it's kind of useful. We're fresh with the numbers, and then we'll talk about what it means for variables. So looking at purely just the numbers, let's say we're considering the greatest common factors between, let's say, 72 and 132. And I want to know the greatest common factor between those two numbers. That can be kind of difficult to determine what numbers go in, if any, are shared between the two. And if I find one that's common, is it the biggest? Is there one that's larger? Is there, can I keep going? How far can I take this? So a way we can actually use prime factorization to nail it down for sure which one it is we figure out the prime factorization, we figure out what they have in common. So let's go ahead and do prime factorization for 72. Off the top of my head, I'm thinking 9 times 8 makes 72. Looking at 9, 3 times 3. Both those are prime, so I'm done there. And if I'm looking at 8, we're going to have 4 and 2. 2 is prime, I'm done there. 4 is 2 times 2, so I'm done with those two. So this tells me that 72 is equal to 2 cubed times 3, ultimately. Or 2 cubed times 3 squared, forgive me, I forgot about the second 3 there. Okay? Likewise, we can take the 132 and break it up into other factors. Which in this case, 132 is divisible by 11 and 12 as a pair. 11 times 12 makes 132. 11 is prime, so I'm done there. 12 is divisible by 4 and 3. 3 is prime, so I'm done there. And then 4 is divisible by 2 and then 2. And both those are done. So 132 would be 11 times 3 times 2 squared. Now, if I look at my ultimate prime factorizations for both of these, I'm going to look at, okay, what do they have in common? Well, I see 1, 3 that they have in common. And it looks to me like, well, this one has a 2 squared, this one has a 2 cubed, which would tell me they both have a 2 squared in them. So 3 times 2 squared. Now, I can kind of turn this back to a number. 3 times 2 squared, where 2 squared is 4. 3 times 4 is 12. 12 is my greatest common factor between these two possible numbers. And we can use our prime factorization to be sure that that is the case. Now this logic applies to variables, or I guess I shouldn't say variables, to monomial expressions. So let's just go ahead and do an example here. Let's say I want to find the greatest common factor between 95x cubed y squared and let's say 25xy to the fourth. Okay, so again, let's just look at the numbers first. We're going to break it up in a very similar way as we did when we were talking about factoring. I'm going to look at the numbers first. Let's make our factor trees. 95 is divisible by 5 and 19. Both of those are prime. Likewise, the 25, 5 and 5. Both those are prime. In this case, we just have the 5 in common. So the greatest common factor between 95 and 25 is going to be 5. So that one is done. Now I'm going to look at the variables. Let's look at the x's. So the one on the left with 95x cubed has x cubed. Okay? The one on the right has 25x. There's only one x there, so I can only say they have one x in common, meaning my greatest common factor of this is going to have only one x in it. That's all they have in common. And then likewise, now I'm going to look at the y's. And I think to myself, okay, what do they have in common? This one has 2, this one has 4, therefore they only have 2 in common. So in this case, my ultimate greatest common factor between these two expressions is 5xy squared. That is the maximum of what they have in common.